Invitation, the session is recorded.
Good.
We may give it one more minute, so since people are still dropping. Okay. Hello, everyone. Welcome to today's seminar, ICT-52 seminar on workshop on 6G systems. In today's session, we are going to have an overview of intelligent networks. Today, we will have 7 seminars from different European projects and also 2 representative companies from Asia and also US. From Asia, China Mobile, and from US, Qualcomm will give an overview on this topic. And we will have a view of different European ICT-52 projects on intelligent networks. This session will start with Hexa-X overview on this topic, where I would hand over the seminar to Markus. Markus, please.
Yeah, wonderful. Thank you very much, Hamed. Thanks everybody for joining. So it is really my pleasure today to give you a talk on Hexa-X activities related to AI-driven communication and computation co-design. So this is an activity which is led by Intel, but of course supported by a number of colleagues, and I mean all of the organizations involved in this work are summarized on this slide. Yeah, and this is an activity that has been documented in an available deliverable. So it's deliverable 4.2 that carries exactly the same name, and I can only invite you to read it. In today's presentation, I will not be able to go into each and every of the solutions and topics we have been addressing inside this deliverable, but I will be giving you a kind of selection of some of the topics, and these are addressing all of the focus areas that we have been looking at in the context of this work. So as you see on the lower part of the screen, I mean the areas relate to network performance enhancement using AI, ML, and 6G. So here we are going to see actually improvements really on the lower layers, so on the physical layer in particular. You know, looking at, for example, the mitigation of nonlinearities. We are going to see 6G network as an efficient AI platform. So here we are looking, for example, at the idea of providing AI as a native capability of future 6G systems, and providing interfaces also to external participants to exploit the AI functionalities. Then we look at solutions for enabling greater 6G network sustainability building on AI ML. And we are looking, of course, at privacy, security, and trust in AI-enabled 6G systems. And here we are in particular looking at possible attacks that may occur in a federated learning AI system and how to proceed in order to mitigate those attacks. And finally, I will be giving a couple of words on some of the demonstration activities. So we are using a federated explainable AI system in order to like online optimize and adapt the deliverable of video content to vehicles in an automotive context. Yeah, so let's start looking into the performance enhancements using AI ML in 6G. So as I said, we will start looking into a physical layer type of enhancements, in particular related to optimization of bitrate and spectral efficiency improvements. When you're looking at the final published deliverable, you will see also additional work that relates to the improvement of end-to-end network operation and management, looking in particular on optimized predictive orchestration based on AI ML approaches. Yeah, so let's start with a very interesting idea on some optimized constellation shaping. So what we are doing here is to use an AI system in order to derive a optimized constellation. As you can see on the upper right-hand screen, it's looking quite interesting. It's an asymmetric constellation, as you can see, and this shape has been optimized in such a way that we can exploit it in such a way that we don't need to rely on pilots in order to do the channel estimation. So that leads, of course, to additional efficiency improvements. And as you can see, we are adding a convolutional neural network in the transmitter chain that will actually be able to exploit the particular shape of this in order to do the decoding without the presence of pilots, but is also able to at the same time do some pre-distortion, taking the PA, so the power amplifier nonlinearities into account, which then leads to the performance gains that you are seeing on the lower part of the screen. Probably I have to make this box disappear. Then the next approach is taking the ML components not in the transmitter chain, but in the receiver chain. And again, what we are trying to do here is to increase the overall spectral efficiency through PA nonlinearity mitigation. And as you can see here, for an example backoff of 4 dB, we see important gains through the neural network-based approach that we have been applying. Just as a general statement, we see, PA nonlinearity compensation as a specifically important requirement for systems that go to higher frequencies. And since in the context of Hexa-X, we are studying systems that also address millimeter wave as well as sub-terahertz and terahertz systems, this is exactly that kind of technology where such solutions will be required. Let's go to the next technical focus area. So 6G so having the 6G network as an efficient AI platform. Here we are going to look at 3 different ideas. So the first one is to have some kind of seamless and pervasive in-network AI operation. So basically designing the 6G network in such a way that it is providing native AI features. And here we will have a look at the AI as a service concept. Then secondly, we will have scalable solutions for distributed AI applications. And here we are looking in particular in federated learning settings. So where local models are being shared by distributed entities and then aggregated in a central server. And when looking at the deliverable, you will also see further information on a compute as a service concept, where, like, similar to the AI as a service concept, we see the whole like 6G system as a system that provides distributed compute entities to users, in such a way that you know, an API is being made available that an external user can actually access and exploit those distributed compute entities. Yeah, so AI as a service, I think this is one of the key approaches that has been introduced in this deliverable. The idea really is, you know, that a user, for example, a smartphone user or any type of external user, is able to exploit the entirety of the network knowledge in order to execute some task. For example, you know, having some model that optimizes handovers when a user is moving from a certain location. So, for example, when driving from Munich to Berlin, to give a simple example. The idea is here, you know, that the problem statement is communicated from the user to the network. The network can actually derive a corresponding model, exploiting the entirety of the network knowledge. But then the nice point is that this knowledge is transferred back to the user without actually exposing the raw data itself to the user. It's only the trained model that is given back. And so it's actually a very nice approach also for network operators to monetize the data that they have available without, you know, exposing the data in a raw format. Another approach that we are looking at is the joint allocation of communication and computation resources. So here we are looking at a problem that we have a number of devices. So on the right-hand side, you're seeing like simulation results where we're really looking at 6 different devices, and each of these devices had different requirements with respect to inference reliability. And then when doing the overall optimization, what we look at is that we have a suitable trade-off in terms of energy consumption, end-to-end delay, and the learning and inferencing accuracy. And also, of course, we are looking at reliability and trustworthiness requirements. And as you can say, we have then an optimized balance across all of these parameters for all of the devices that are participating to this setup. Now, the next topic is on AI ML as an enabler for 6G network sustainability. Yeah, and so what we want to achieve here is really to exploit AI and ML to reduce the overall complexity of the network implementation with sustainability objectives. Of course, we are looking at frugal AI and ML. So, in particular, in the context of scenarios where a constant update of the AI model is required, and the training phase must be designed in such a way that is sustainable. And then again, when looking at the deliverable, you will be able to read about further approaches that we are looking at, in particular at semantic communication. So where the idea is to basically exploit context information at the receiver in order to have a more efficient way of communicating, like a minimum number of information from the source to the destination, enabling the destination to reconstruct the exact symbols of the source. So let's start with a quick overview on RIS, so reconfigurable intelligent services. So RIS is actually one, I think, of the very hot topics for 6G, bringing really like a very novel approach into the picture. So what we are really looking here at is a problem in the sense that in a RIS setup, we really have a large number of passive elements without any sensing capability attached to each of those elements. So what we really need to do is to have to design actually an optimized channel estimation method that is based on a sparse representation of the channel, right? Because I mean, we are not able to have access to the very detailed information for each and every data point. And a neural network is then used to estimate the corresponding angular parameters. And as you can see on the lower right-hand side, we achieve very good results with respect to our neural network-based approach over traditional least squares estimation, for example. But you see also a bit of challenges. So on the left hand lower image, you see this kind of saturation effect in the red curve, right? And this is actually due to power leakage, you know, because of grid imperfections. Yeah, then the next topic I want to introduce to you is related to over-the-air model learning for frugal and resource-efficient network AI operation. So what we are really doing here is to look at over-the-air learning in the sense actually that you know, we have a number of entities that contribute to this learning context. But what we really need to identify is the significance of the different data points that can be provided by the different entities. And significance can, for example, depend on the location of the source of the information. Then we are looking at different methodologies for identifying the level of significance. So this can be based on kind of a priori or a posteriori methodologies. So as you can see here in these illustrations, we look at approaches for data significance pre-evaluation or post-evaluation. Right, and we are basically then deriving the most optimum way of making sure that exactly that data is being shared that reaches the highest levels of significance. Now let's also have a look at privacy, security, and trust. So here, actually, we have a topic that is currently very high also on the agenda of the European Commission in terms of regulation. You know, we have, for example, the AI Act, where cybersecurity and privacy plays a big role. We have the Cyber Resilience Act that is currently being discussed, etc. So we are looking at the way of countering cyber attacks that occur actually in particular in AI ML context. We are looking at trustworthiness aspects and similar metrics that are important in trustworthy and privacy in an AI context. Yeah, so let me have a quick introduction into the security mechanisms we are looking at in the context of federated learning. So in this context, we have like distributed entities that provide local models to a centralized server. And here we can see different types of attacks. So, for example, a malicious user can provide incorrect data to the server. A malicious user may actually want to alter data that is provided by, or alter models that are provided by other clients. And what we need to do is actually to mitigate those effects. So we are looking here at solutions that apply, for example, a methodology of requiring that the different models are being forwarded through multiple hops in a certain way, also applying certain encryption schemes. And we are basically showing that by applying the methods that we are defining here, we can exactly mitigate the effects that I have mentioned. Then another topic I would like to briefly talk about is about explainable AI for radio network control. So and just to say, I mean, a quick word on explainable AI. This is of course a very big topic. So typically, like deep neural networks are being considered as kind of opaque or black box type of models. So we are looking at a way of opening up those closed models, or basically another way is to apply intrinsically interoperable, intrinsically interpretable solutions, for example, based on rule-based systems. So we are looking at both. So what we are doing here is we have been performing experiments on performance management data that was derived from radio access networks. We have been applying a 15 minutes granularity in order to derive our data. And we have actually been using such an explainable AI system with the objective to explain and derive the effect of network configuration and user device load to predict and optimize network performance KPIs. And as you can see in the lower right hand table, actually we in particular observed that our new models give a greater attention to timing advance parameterization of the network. Now I'm a bit running out of time, but let me give a few words on the demonstration activities that we are engaged in. So we are having a demo on a so-called federated explainable AI system in an automotive context. So we have different vehicles and users inside these vehicles that are providing data, to a centralized server for quality of experience, or QE forecasting, that is then being exploited in order to adapt the quality of the data stream to the different users. And I mean, this is in particular important for applications such as teleoperated driving. So where a kind of remote driver is receiving the video data from the vehicle such that the remote driver can take over control of your vehicle, right? And of course, we can only transmit so much information and such a quality of the data stream as it is being allowed for by the local configuration of the network, and that's exactly what we are doing here. Yeah, so as a quick conclusion, I believe that we have been showing that AI/ML can provide substantial improvements to a 6G system, and is likely going to be a key differentiator of 6G over 5G. I mean, we have been looking at a number of technical focus areas. They are listed again here, and I mean, we are going to provide and publish further details in deliverable 4.3 that is going to be available end of April. And that's all. Thank you. Any questions?
Thank you so much, Markus, for a nice overview of this topic. So there are a few questions. So I guess we have time for one of them, and then we can return back to question offline, the rest of them.
Yeah.
So there is a question whether AI as a service would be limited to network task or for more general purpose users as well. So
it's a very good question. I would say, definitely it can be used as a network task, but our vision is actually to make this available also to clients, right? For example, smartphones. So as I said, for example, imagine you're driving your car from Munich to Berlin. You want to get a model from the network that allows you to constantly adapt to the best network configuration, doing like handovers ahead of time, for example, that is exactly the type of application we are envisaging. So you are basically requesting the model from the network. The network uses its entire knowledge in order to optimize the model, and the vehicle is then receiving this information, but without requiring the network to expose actually the raw data, right? It's basically hidden in the model that is being conveyed to the user. I hope this is helpful. Yeah.
Thank you, Markus. So yeah, it is in the vision that the networks would not only provide communication services but also compute services and like
exactly.
the AI services and so on.
Exactly.
Yeah, I see there are a few more questions, so it would be great if you can return to them offline. So for the sake of time.
Absolutely, I will. And thank you very much for the opportunity to present.
Thanks a lot. Thanks a lot. So I think we can go to the next presenter from Dedicat 60 project. So Drazen, please free to share slides. So yeah, we see the slides, so but we cannot hear you yet.
Yes, it's okay now.
Yeah, your voice is quite weak. So
Let me just check some settings. That would need to be okay there. Is it quite better?
It's better now. Yes.
Okay, so I will try to keep that. Just to put more volume. I hope it will be okay. Okay.
Yeah, much better. Thank you.
So you can confirm that you are seeing the slides on the screen?
Yes, it is clear.
Okay. So good afternoon, everyone. Drazen Ribar. I'm working for AIRBUS. I'm partner of the Dedicat 6G platform, Dedicat 6G project, which is an ICT-52 project. I'm responsible of innovation project within AIRBUS, working on European project, but also in projects which are invested by AIRBUS or by other kind of partners. Within the Dedicat 6G project, we lead the proof of concept and demonstration activities, which is part of the work package 6 within the project. So this morning you have a presentation of the Dedicat 6G project based on the architecture side. So here I will just present you about the integrations, the evaluations and measurement, and the demonstrations and showcasing of the project. So this is the agenda through which I will go this afternoon for the project, having a short overview of it, sharing about the challenges and the neighbors, a short view on mapping of KPIs and key value indicators related to the project. And I will finish to go through the different use cases we have identified, and we'll go through in terms of evaluations and demonstrations in the project timeline. So just an overview of the project. So Vera Dr. Vera Stavroulaki from Wings ICT Solutions in Greece is the coordinator of the project. We are 14 partners from 8 different countries. The project is in its third year of activities, so meaning that this year it will be the last year of the project. And also we have an agreement to collaborate with 5G PPP working groups. The different challenges of the project. So we have identified 4 challenges. The first one is about the dynamic distribution of intelligence. The goal is to reach the everything as a service and the human-centric applications requirements in terms of not zero latency, but imperceptible latency, energy efficiency, and the optimization of resources. This will be done through the work on intelligence for computations, communications, and storage, which are becoming increasingly critical for the users of the networks. The second challenge is about the dynamic coverage and connectivity extensions. The goal is to make the equality of access to the network, depending on where we are and the need of access to the networks, as it could be in urban, non-urban, through the events or for critical purposes, to have access to through one area to the network. The third challenge is about the trustworthiness cybersecurity threats in terms of also security, privacy, and trust. As in a more open world in terms of networks based on the IoT, the use of edge, the different nodes, we need to have and to apply more trust and privacy and security to ensure that by the end-to-end or end to the system, we will not have threats which will be able to block or to decrease the capabilities of networks. The last challenge is about the human in the loop. So the goal is to bring novel human-centric applications and interactions to the users based on the three first challenges. And this is also to support the capabilities of novel techniques in this project for the use of the network. The technical enablers. So we are 4 technical enablers. The first one, so each one is responding to the different challenges. The first one, and all of them are also linked to a work package within the project. The first one is about the mechanisms for the dynamic distribution of intelligence, where the goal is to bring the different capabilities to address the computations, processing, or storage, and to put the optimizations of resources where we need in terms of network resources or services resources. The second one is about the mechanisms for dynamic coverage and connectivity extensions, where we want to exploit some new innovative devices based on drones, robots, connected cars, and other kinds of mobile assets in order to address the capability to make the users to be covered by the networks and to have the access to the network, and also to allow these kind of mesh capabilities by the long distance and to be connected through the networks. And with the benefits of beyond 5G and 6G to continue to maintain this imperceptible latency for the users. The third one is about the security, privacy, and trust. So we want to put a lot of trust and security purposes, especially in the case that bringing the 2 first mechanisms based on the edge node and also on some devices to allow the coverage extensions or for the network, for the intelligence and for the resources optimization to secure the different layers and to secure also the use of the networks by the users and to ensure their privacy. The third one, which is the novel applications and to bring some new use and new integration of tool or applications or services for the users. So this third technical enabler is part of the work packages for which we are in charge as a leader. We can see some example of novel tools which could be used in terms of augmented reality, smart glasses, connected cars, robots, etc. Before going to the use cases, I would just make some we'll say some summary about the use of technical enablers and the mapping with the sustainable development goals. So for each technical enablers, we are addressing some development goals based on the United Nations and the same regarding the European Commissions. More or less, there are some some SDG which are similar, but the goal will be to ensure the safety. Depending on the case, you are using the networks to include, so it's in terms of inclusivity for the people, also to address the industry part, the critical capabilities and the safety and security of society, and also to address the energy consumption. What we have done, we have made also the mapping between these KPIs and KVIs. So for each use cases. So here we are a presentation of the different use cases, and we will go just after through the different use cases. So the first use cases with the KPIs we want to address for each use case, and how we address these key value indicators depending on the KPIs and the use case. As an example, the goal would be to optimize by automations, to optimize the various automations and to ensure the safety of warehouse worker. To enhance the end user's experience during the large event, like a concert or some home. To also to increase the reliability and resiliency of communication network for public safety, for support them in the response of the crisis. And in the smart highway to bring not only vehicles but all the users of the road, including bicycles, pedestrians, etc. Here we have just a summary about how we address these different challenges in terms of inclusivity, as we are bringing the network everywhere and anytime. Safety. It could be the protection of users, as also supporting through the public safety use case, the security and the safety of the citizens. The connectivity, as maintaining the access to the network when needed, and the contribution to the environment, especially as we are working on an dynamic and intelligent resource positioning or coverage extensions. We are not using the resources at any time, but when just needed from the user's view. So through the project, we have identified the 4 use cases. The first one is about the smart warehousing, which we will be evaluate and demonstrating collaboratively between Greece and Serbia. The goal is to use artificial intelligence to optimize the warehouse operations and to make to leverage the efficiency of the different workers into the warehouse, and also to enhance the safety of the personnel and goods, and to offer the capability to use so automatic chain in logistics in order to reduce time for logistics. The second use case is about the enhanced experience, especially during live streaming features used by the people during a large event, for example, a concert or some other kind of event, and also to increase the user experience when sharing in real time, in participating or in receiving the stream, because far from the scene or not part of the event. In the public safety use case, which is the third one, so the goal is to foster the resiliency and reliability of the network, which is one of the main points for the PPDR users and first responders, and also to have always connectivity available in order to continue to respond and to support the different people and the citizens during the crisis. The last one is the smart highway, which will be done in conjointly in Belgium and in Germany, and where is not only to allow and to bring this low latency between the vehicles, but also to share the road usage to all the road users, as mentioned previously, about bicycles, about pedestrians, motor buses, etc., and also to foster the security for all the users. So in this first use case, smart warehousing, the need from beyond 5G and 6G network, which is defined in the different deliverables and in the architecture as KPIs, is about the latency and the reliability for the data and the interactions based on the robots used in the warehouse. The high throughput video stream for the surveillance, and the high location accuracy to guarantee the positioning of the robots and the assets. So in this, we will mainly use the different implementations we have done in intelligent distribution of resources in order to bring the capability to leverage the use of a novel system or novel tool in the warehouse. During the first period, we have made some evaluations. Here there is some example of the evaluation done, which is one of them is about the latency relative to the context of the network in outdoor 5G, indoor 5G, and Wi-Fi. So we have a better use of 5G in indoor, outdoor, and based on the VPN and the Wi-Fi connections. Also, the latency depends in the context of a bar metal or a Docker. And what we can see by the use of intelligent distribution of resources, what we have and direct impact on the energy consumptions based on the third graph and the bottom of the slide. So for the third period of the project, so this is the last one of this year, 2023, we will run a second pilot demonstrations, which will be in the current spring of this year, and we plan to have a final demonstrations at the end of the year before the end of the project, where we will demonstrate the full component integrations and the evaluations in the real environment in Serbia. Related to the enhanced experience, we will use some devices, so legacy devices are smartphones, bring some virtual reality devices, or like smart glasses. So what we are working there, based on the intelligent distribution of resources, is how we will enhance the user experience. So making by the use of smart glasses instead of smartphones to also help people to better benefit from the event and not to use the smartphones and have a view of a lot of smartphones through the event. To demonstrate that using some novel tools, it will be better as an user experience, and to leverage the user experience for the people who are far from the scene or not participating to the event, and to by the use of virtual reality devices to make them as they are present to the event. As the same, we have some example about the different evaluations we have done during the project for the use case 2. Which is also based on the map placement for the coverage scenarios. And what we can see also is the difference between the use of the specific tools for the projects, or based on the legacy on the commercial tools like smartphones. As the same from the first use case, and it will be similar to the other one, we will have a pilot which will be conducted in the spring of this year. So for this use case, it will be in Finland at Oulu University, and we will proceed to the evaluation and measurement of the overall development of components. For the third use case, for which I'm more confident, as it's part also of the AIRBUS objective in the delivery of critical communications for the public safety users as PPDR and first responders. So from the beyond 5G and 6G, we want to bring so extremely reliable and efficient communications, and making the infrastructure availability anytime, anywhere. I don't think I need to re-explain, as for first responders and PPDR users, it was very critical to be able to communicate and to share the situation awareness during the response to the crisis. Through this use case, we will use all the components from the intelligent distribution of resources in order to have a better placement of the different resources and services, and the coverage extension also to bring the coverage capabilities where the first responders will need in order to be connected and to share with all the organizations about the crisis. What it's novel also for us through in this point. So we are moving from the legacy PMR solutions to the 3GPP MCS solutions, and from these 3GPP MCS solutions, we are deeply engaged in the evaluations of a splitted architecture for the use of the project. So mainly we will evaluate and measure that we will not decrease the standard in terms of capabilities, but also we are able to leverage the capability of the network. Here there is an example of what we have started to evaluate, more about the latency, and that we have a better latency by using the 5G connectivities, beyond 5G connectivities, and what we will demonstrate that we will have no perturbations in terms of loss of connectivity. And during the loss of connectivity or when the system will detect the loss of the connectivity, we'll be able to readdress. So bringing the coverage if need coverage, bringing the service in terms of mission critical services to the users, and the perceptions for the end users is that the service is there is no interruption in terms of the service. So they will continue to see the video.
Sorry for the interruption. You're a little bit over time. So
okay, so I'm just finishing there. So okay, thank you.
Thanks.
So for the third period, we will have this integration of the different mechanisms and to make the evaluations and the measurements and to demonstrate, to make a demonstrations at the same time in the spring. The last one is about the smart highway. So I will not, to be just really fast, go through that. The slides will be available. As previously mentioned, we have delivered the deliverable D6.2, which mentioning all the KPIs we are running for that. But just to show that in terms of addressing the road users, we make, as we can see on the picture on the left, the detections of all the users of the road by the different devices available near this corner, which could be smartphones, connected watches, etc. And one of the goals in terms of novel interactions and human application. Novel interactions and new future applications is not only to give the information to the vehicle. There is some other users of the road close to them in order to decrease the risk of accident, but also based on the very low latency of 6G, to bring and to address the pedestrians, for example, as we have in the use case, as the capability to show and to highlight the risk of collisions because there is some cars in the surrounding of the pedestrian. So thank you, and sorry for having going a little bit far from the time. So if there is some few questions, the rest I can address through the chat if needed.
Thanks a lot, Drazen, for a nice overview of the dedicated 6G projects on this topic. So it was very interesting to see how AI could be used for different type of resource allocations to enable extreme use cases in different scenarios. So it was very insightful. I would encourage everyone to raise questions in the chat if there is any about this seminar. So, and by this, we could go to the next seminar where thanks a lot, where Ignacio will share the view from Hexa-X projects and using AI for orchestration and management of future 6G networks. Ignacio, please.
Yes, good afternoon. Thank you very much. Can you see my screen?
Yes.
Okay, perfect. Okay, this is Ignacio, Labrador, Pavon. I'm working for Atos. I'm here representing Hexa-X Work Packet 6, as you can see. Well, let's go to the very beginning. Why machine learning? I mean, in general, and not only for services management and orchestration. Okay, the problem is that the regular software development workflow is only applicable to easily explainable and those problems where data and parameters are fully clear. I have represented here a very simplified workflow regarding the typical software development. All of us, we are familiar with this. Typically, we have a problem to solve. Then we need to think on the problem, considering the relevant data. Then based on that, we generate an algorithm. And of course, we try to make it run in the target environment. But the problem is that for certain kinds of problems, it's not always possible to work this way. I have summarized here some paradigmatic, let's say, problems in the machine learning scope, like natural language processing, handwritten characters recognition, weather forecast, stocks price evolution, images recognition, and many more that cannot be addressed. We have seen that cannot be addressed in using this typical software development workflow, and this is because of different reasons. For this kind of problems and other similar problems like this, we could have huge amount of data, we could have raw or unnormalized data, especially we could have hidden variables that are not fully clear in the scope of the problem, and also without a clear relationship between them to figure out what are the relationships and how the algorithm should behave to deal with that problem. So for certain problems, it is not always possible to generate an algorithmic solution, at least in an easy way. So machine learning, as we know, can help us with this and can generate algorithms able to efficiently address these more complex problems and dealing with huge, incomplete, noisy, and or unstructured data sets. So, okay, where is complexity in our scope regarding management and regarding services management and orchestration? Well, in Hexa-X Work Packet 6, we have identified these three areas where we have more complex problems and where machine learning can be applied. This is what we call the continuum management and orchestration, also time series processing in our scope, of course, and the operations management. I will introduce them in the following slides. The first one, what we call the continuum management and orchestration. This is related with one of the main innovations we envisage for 6G is the integration of new technical domains from the management and orchestration perspective. I mean, not only considering the core network or the edge network as we do for 4G or 5G, but also other new domains, and especially what we call the extreme edge. The extreme edge are all those devices at the end user scope beyond the radio access network. Okay, and this new domain that we want to manage and orchestrate as well. We want to manage and orchestrate services on them is very special because we are not anymore talking about a very controlled environment like the one we have at the mobile network operator scope. Here we are talking about those devices, for example, in vehicles, in factories, or in general at the end users and the end user premises, and we can consider this a kind of uncontrolled an asynchronous environment. Those resources sometimes are battery power or can be switched on or off unexpectedly. And this is, of course, a problem from the management and orchestration perspective. Also, we could have unpredictable mobility patterns, high heterogeneity of devices, as you can see here, and very important from the machine learning perspective. This ecosystem is massive in scale. We could have a big amount of devices with different characteristics. This is one of those factors increasing the complexity I was mentioning before. And from the operational perspective, this can even exceed human scale. So automation algorithms driven by machine learning algorithms can be very helpful here. Here in this slide, I have summarized some possible uses of machine learning in this scenario, considering the continuum management and orchestration, this multi-domain integration. The general idea is that having access to this high diversity of data sources in the core, edge, extreme edge, and other networks, this makes it possible to collect and correlate a rich variety of heterogeneous data, which allows implementing new management and orchestration strategies. For example, we could implement automation algorithms integrating heterogeneous information from the different domains. We could generate models able to work with those user requirement raw or unstructured data to trigger orchestration actions based on that. Machine learning could support also big data analytics algorithms. We could also use machine learning to manage this volatility I was mentioning before regarding the extreme edge devices. For example, using predictive algorithms to predict future state of devices or their energy requirements. Also, we could implement optimization algorithms for the network functions placements. You know, this is a well-known NP-hard problem, and especially considering the continuum of the network. So in summary, machine learning techniques could be applied on both within each domain, even in a very granular way at the level of individual devices, but also globally through this continuum orchestration function we have here in the figure, integrating data from the different domains. Okay, this is the second source of complexity I was mentioning at the beginning, is regarding time series processing. We know that certain machine learning algorithms have demonstrated a very good performance in dealing with time series. In general, the variation of these metrics over the time can be treated as time series, of course, and in our scope, those metrics could come from, for example, from the infrastructure. But what is interesting here is also to include also the service layer to make possible to correlate data from different sources and to make the machine learning systems able to extract valuable information that could be used to trigger management and orchestration actions. I have included here some examples where machine learning could be used in this scope, for example, for hidden patterns discovery related to non-evident causal relationships on multiple time series. Also to implement proactive elasticity management and orchestration algorithms to anticipate the enable, disable, or scaling of network functions, and also to support proactive network functions placement decisions. Also to optimize the network resources usage as well in a proactive way. Here on the right-hand side, I have included this high-level picture illustrating this idea. Machine learning driven management orchestration system could be used to correlate to discover and correlate events from very different scopes. For example, some events A, B, C, D coming from infrastructure metrics, but also to correlate that with metrics coming from, for example, road traffic control cameras or web services or whatever, to practically generate orchestration actions, and in this case, for example, to migrate certain network functions to certain edge or extreme edge resources. Another source of complexity is the operations management. In this regard, we have two aspects. We have AIOps and MLOps. AIOps represents the application of machine learning to the well-known DevOps paradigms coming from the cloud-native architectures. The target here is to efficiently operate already deployed services. Here, the focus is on the operational side of the well-known DevOps loop. Operated services in this case can be AI ML based or not. This is focused to any kind of service, and the focus is on monitoring, automation, and service desk. The complexity here, that is the justification for using AI, as I was commenting before, is in the huge and diverse amount of information to be processed. And also another source of complexity is the integration of the information coming from different operational tools. Intent-based service management, that is also one of the innovations we are addressing in Hexa-X or Hexa-X, can be also considered part of this AIOps scope. On the other hand, we have also MLOps. MLOps can be seen as the opposite to AIOps in the sense that it represents the application of DevOps to machine learning to develop and deploy machine learning models. We can understand MLOps as a kind of specialized DevOps, but targeting this development and deployment of machine learning models on the network. As you can see here in the figure, what we have is an extended DevOps loop, including this third loop on the left-hand side, the ML loop, that is intended to include in the workflow the learning stages and the collection of data that is necessary to implement the machine learning models. So yes, what is represented here is a kind of extension of the regular DevOps workflow, including this learning stage that is necessary for machine learning system. Of course, the approach will be different depending on the machine learning paradigm to be deployed on the network. Okay, main challenges associated to using machine learning for the services orchestration. This is a summary of what we have in our previous deliverable 6.2 in WordPack X6. As you can see, and sorry for this slide, it's a bit wordy, we have many challenges regarding the learning stage itself. Since I don't have much time now, I'm going to jump directly to items C and D, because A and B, computational complexity and training data availability, I think all of us, or most of us probably are already familiar with that. We need sometimes specific computational resources for training the machine learning models, and also the access to data can be challenging in some cases, and especially in our telco grade environment. Regarding item C, we consider it is also a challenge the way the learning stage is introduced in the regular mobile network operator workflows. This is related to the MLOps concept I was introducing before. And this is because in the telco grade environment, the network services, as we know, are typically designed and developed outside the mobile network operator scope. So data that is necessary for training sometimes need to be shared with third parties, and this could lead to data privacy and security issues. Some machine learning paradigms where learning happens directly on the mobile network operator premises, for example, federated learning or reinforcement learning models could help to deal with this challenge. But of course, this is not applicable in all cases. In other cases, when it is really necessary to share data with third parties, of course, encryption techniques should be applied, for example, homomorphic encryption techniques. Another challenge, this is item D, is to what extent is it acceptable for a service to run in a production environment without the training being fully complete. This challenge could be addressed by really activating the service to really putting the service into production once it is considered the training stage is complete or at least complete to an acceptable level. But perhaps this is not valid in all cases. For example, reinforcement learning models need to actually interact with the real environment to be trained. Probably there is no general solution for this, and the solution will depend on the criticality of its particular service. Another challenge is explainability. We know that data structures generated by AI/ML models consist typically in sets of long sets of numbers. So unlike traditional software programs, this makes it difficult to understand the logic in these models, which are commonly seen as kind of black boxes. But in case of a relevant event or a failure, the operational logic could not be easily explainable. A possible way to address this challenge could be addressed using the so-called the explainable AI paradigm that has been mentioned before, which can be used to find the underlying rules behind the AI/ML algorithms. We are not addressing this concept specifically in Work Package 6 in Hexa-X, but as we have seen, other work packages are taking care of this. Also, another challenge are the possible failures that could happen by using AI/ML systems. As you can see here in these funny examples, even our human intelligence cannot properly classify real-life patterns sometimes. But in our case, we need to build practical systems able to take real-life management and orchestration decisions. And in case of failure, this will impact on the service provider reputation. Probably there is no general solution for this. Software failures is a common fact in software, not only AI/ML. But in the case of AI/ML, probably there is no general solution, and the usage of AI/ML techniques should be considered for its network service. And probably for those that are considered critical, it should be considered that humans should be always in the loop to decide if certain orchestration actions should be really performed or not. This is my last slide. I would like to introduce about the demos we are addressing in Work Package 6. In Work Package 6, we are now in our final stage. Previously, we developed our management and orchestration architectural design, and now we are working on the development of these two demos to demonstrate these concepts I have introduced here and others, of course. We have this demo number 4, demo number 5. Demo number 4 is about orchestrating a service to control a set of real-life robots in a simulated industrial scenario. We consider
a bit over time, Ignacio. Sorry for interruption.
This is my last slide. Few seconds. So we consider the robots as part of the extremettes, and we orchestrate the service considering these extremettes and also other resources in the network. We are developing the predictive orchestration algorithms associated to this service. And the other demo number 5, this is here we are developing also a service that relies on a reinforcement learning algorithm to control the traffic lights in a simulated urban environment. As you can see here, the target is to increase traffic flow and reduce traffic jams. We have also an implementation of the streamheads based on Raspberry Pis and a set of LED lamps to simulate the traffic lights. And we are targeting different aspects, as you see at the bottom in this demo, like security, MLOps, and also prediction-based algorithms. And that's all from my side.
Thank you so much, Ignacio, for a very nice presentation and sharing the insight from Hexa-X project and how AI could be differently used in several different ways in management and orchestration of 6G networks.
Thanks to you for the opportunity to present here.
Right now, there is no question dedicated to this seminar, but if there is any question, I would encourage everyone to raise the question in the chat, and we could address them offline. By this, I would like to thank you again for a nice seminar. We can maybe continue with the next seminar from DAEMON project to share their insight on machine learning-based resource allocation for orchestration of the network, somehow relevant to the previous seminar.
Hello, everybody.
Hi, Danny.
Hi, can you hear me? Can you see the slides?
Yes, it is clear, so please go ahead.
Okay, thank you. So as announced, this is a presentation of the DAEMON project, some work that we've done within work package 4. So this morning you already saw a presentation of the DAEMON architecture. This is a presentation about one particular component of it, namely how to organize the self-learning Mano. So I will first present a little bit of context. Then I will show that resource optimization is important in two aspects, and when you have to initialize a new network service, or you want to scale it up or scale it down. I will present briefly the existing solutions and the traditional and machine learning techniques that were used to tackle these problems. So some typical results. I will not have time as in all the other presentations to go in very much detail, but I will point you to some papers where you can find more information. And finally, I will draw some conclusions. So, well, I guess everybody in this audience knows that in the 5G context and probably in the 6G context and beyond, you can set up network services, in particular network slices on the fly, and you can tear them down also. So typically what you have to do is to launch a certain number of virtual network functions, can be a UPF, an AMF, or an SMF. We've seen all these virtual network functions in previous presentations already, and they need to send traffic to each other. Typically, it is encoded in a so-called service function chain, which is a collection of VNFs that exchange information with each other. So, and since these VNFs require some resources and there is a virtual infrastructure available, we need to decide where these VNFs will run and how will they communicate, and how the traffic flows that run between these VNFs need to be routed over the network. So when a new network service needs to be set up, we have two decisions to make. We need to place the VNFs in certain servers in the data center, and we need to make routing decisions. And once this network service is set up, we need to monitor if the KPIs are still within the bounds. And if not, we need to take action, and we need to either add resources to the particular VNFs or remove resources of some of them that are not used that much. There are various implementations of this already. Kubernetes could be one of that. Open Manos would be another. But typically what they do is to launch or to write a script with which these VNFs are launched, and there is not much automation in there. And in particular, Kubernetes does the scaling by looking at some KPIs, by monitoring some KPIs. And if they surpass a threshold, they either remove a VNF. Okay, so this is the context. Let me zoom in a little bit more in detail on the two specific problems. I want to explain them from a contextual point of view, and then delve into the solution methods that were tackled, that were used to tackle the problems. So first, the initialization. So this is typically a graph-in-graph embedding problem. So I have a graph, a mathematical object, a graph that represents the infrastructure, and the vertices, the nodes in that graph are the servers and the routers, and the arrows or the edges in that graph are the links that are available in the network. So that's the bottom graph, and on the top graph, this represents the service function chain, and the red rhombuses are the VNFs, and the green dotted or the green dashed arrows are the traffic flows that need to be supported between those VNFs. And so typically what you need to do is to embed the SFC graph into the infrastructure graph, something like that, like you see here. And in order to do that, you typically need to define some decision variables, and you need to have a set of decision variables that determines where the VNFs are placed, and a set of decision variables that decide how the traffic is routed over the network. And you cannot do that randomly. You need that some constraints need to be obeyed. So, for instance, the decision variables that determine where a VNF is being placed needs to express that a VNF can be placed on one server and one server only. There are many of those inherent constraints. There are also constraints associated with the resources in the network, and the resource demand should be always smaller than the resource supply. So the resources that are available in the infrastructure should never be overconsumed. That's another set of resources. And then, another set of constraints. And finally, there is also a set of constraints associated with the KPIs. So, for instance, it can be that the delay over the network or the delay associated with the network service cannot be larger than a certain amount. So here you see the two types of methods that are used to tackle this. Traditionally, such a problem was formulated as a mixed integer linear program. Well, nowadays it's not linear anymore because most of the constraints are not linear anymore. But anyway, this is just a name. And typically, what you do is you define a function that needs to be optimized. For instance, the cost of exploiting the network or the delay that needs to be minimized. And then on top of that, you define all these constraints in mathematical form. And then once you have done that, you run it through a program like Cplex or something else, and it provides you with a solution. There are two problems with that. The first problem is that this is an NP-complete problem. And in human language, this means that it's if the size of the problem increases, so if the number of nodes in the network increases, if the number of VNFs in the service function chain increases, the computational time typically increases exponentially with that number. So if the problem size becomes too large, it's computationally untractable. That's the first problem. The second problem is that if you formulate it like that, you need to know all the parameters that go into the constraint. So basically, you need to know how the network or how the infrastructure will evolve over time. You need to know how much resources there will be available 5 minutes from now, and you need also to know how many resources the new network service will require 5 minutes from now. In principle, you do not know that, and typically what is done is to take worst case assumptions such that you're guaranteed or virtually guaranteed that this is always the case. So in order to tackle these two problems, this problem was also formulated as a reinforcement learning problem. And here you see the typical structure of a reinforcement learning loop at the right, on the right. So typically what you do is you have the state in which the system is, the network and the new network service that needs to be set up. You acquire that state, you feed that state into a policy, and that policy gives you an action. And based on, well, that action is that implemented, and if that action has a good result, you get a high reward. If that action gets a bad result, you get a low reward. And gradually you can adapt or modify the policy in such a way that the reward that you get increases. So that's in a nutshell what reinforcement learning does. The particularity of this problem here is that probably the state, all the state information is not available to the agent. It's not possible to acquire all the loads on all the CPUs and the servers of all the data centers. So you need to summarize it in some way, and therefore the problem needs to be formulated as a partially observable Markov decision process, while traditional reinforcement learning is formulated as a simple Markov decision process. So this complicates the matter a little bit, but not too much. The only thing that you need to do is to take into account also the history. It's not only the observation now that's important, but also the past observations that come into play. This slide summarizes more or less what I already said on the previous slide, that with MILP, the MILP solution, mixed integer linear programming solution, you typically need to make worst case assumptions. So what you don't want to do is to go to the forbidden zone, and the forbidden zone is the zone in which resources are overconsumed. And so the arrow, maybe I'll show my pointer. This arrow here, this arrow represents the resource availability, and this arrow represents the resource demand from the new network service. And you need to end up in a point that does not lie in the forbidden zone. Otherwise, you're going to reject the request for the new network service. And since you have to make a worst case assumption for both, you end up with a very prudent system. With reinforcement learning, you can gradually learn how the network will behave. You will know the behavior of this arrow and the behavior of this arrow, and hence you can make better decisions. Of course, this is a two-dimensional representation of what is in general a multi-dimensional problem. But anyway, I hope you get the gist of it. So here I present some results, and more results are presented in the paper that I cite here at the bottom. Here on the left, you see the performance of the mixed integer linear programming, and here in the middle, the performance of the reinforcement learning approach. And there are two types of metrics that you see here. So what you see is how the system behaves as time goes on, as the training proceeds, in fact. So there are two kinds of metrics: the rejection rate, which is indicated by a graph by line with crosses, and the violation rate, which is a line with circles. So the MILP approach does not have any violations by design, because we have taken that worst case approach there, but there are many rejections. The reinforcement learning approach, after some training, levels off to a situation, or levels off to a lower value of the rejection ratio. Of course, there are a little bit more rejections, but you can reduce those rejections by penalizing. You can reduce those violations by penalizing violations more. But of course, then the rejections will go up again, but not as much as the MILP does. That's the first advantage of the reinforcement learning approach. The second one is that the inference time that you see here on the right. So this is the time to make an inference for the three cases that we have considered. So for reinforcement learning, it's much lower than for the mixed integer linear programming. And for the deep reinforcement learning, we pay a little bit more penalty, but not much. So deep reinforcement learning is just reinforcement learning in which the policy is implemented by a neural network rather than by a table. Okay, so all this was related to embedding a network service in one data center. If you need to implement it over various data centers, you need to make an additional decision. You need to say which parts of the service function chain go to one data center and which one go to the other. And therefore, we have looked at distributed multi-agent reinforcement learning approach. And here you see a typical example. Again, I don't have time to go in detail, but the results and the procedure are reported in the two deliverables that I mentioned at the bottom. One is already available. The other one is becoming available in March. So here you see a typical example where you have 5 data centers. Each of these data centers has its own agent, and these agents can make 3 decisions. They can say, I want this VNF, or I do not want this DNF, or I'm impartial to this DNF. And here in these 2 graphs, here on the right, you see how agent 1 and agent 2, I only show 2 of them, but the 5 agents have a similar behavior. You see how these agents make their decisions. So in the beginning, they do not know anything. So they make a random decision. So they, with a probability of 1/3, they say, I want it, or I don't want it, or I'm impartial. And then gradually they learn to make good decisions. So these blue curves indicate the number of times that the agent makes an acceptance decision when he should make an exception decision, the number of times he makes a rejection decision when he should make a rejection decision, and these red curves are the opposite. He makes a rejection decision, but he should have accepted, or he makes an acceptance decision and he should have made the other decision. So the red curves ideally should go to 0, and the blue ones ideally to 1. We are not there yet, but at least it's learned something. So this is work in progress. So now let me go to.
Excuse me, Danny. So
yeah,
we are a little bit behind the schedule. So may know how much time.
According to my clock, I'm busy 13 minutes. So maybe a couple of more minutes, 3, 4.
Yeah.
Okay.
Sure. Yeah. Thanks a lot.
So let me turn back to the VNF scaling approach. So there the network service is already set up. And then we need to monitor the resources and monitor the KPIs and see if we need to change something in the setup. This is typically a tracking problem, and in the interest of time, I will not go in detail, but typically you have an amount of work that is presented to the system. The system then reports its latency, its KPIs, for instance, latency and its load, and then the controller needs to decide if more resources need to be assigned to do that work. It's a tracking problem. Typically, if you would have lived 50 years ago, you would have tackled this with control theory, used a traditional PI controller, but this was also we have also formulated that in a reinforcement learning framework. I'm not going to go in detail because it's very similar to the procedure that I already explained when I talked about initialization. The results are reported in 2 papers that are cited here at the bottom. So I briefly show you some results. So this is the performance of a PI controller that is tuned optimally, and this tuning is a nightmare. The system is not linear, so there is no theory to tune it. So basically, you have to explore the whole parameter space, but once you have tuned it, it almost works perfectly. So here you see the amount of work that is presented to 3 VNFs, and here you see how the number of CPUs, virtual CPUs, that are assigned to do that work. And the delay is more or less under control, except for some peaks. Here you see the comparison of the PI controller, which is this rhombus here, and the reinforcement learning controller, which are all the circles. And you want to be here in the bottom left, because then you don't make any violations and you have the least amount of virtual CPUs. to be allocated. The reason that there are many circles is that because we ran the reinforcement learning with various parameters in the cost function, or in the reward function, I should say, and it's a little bit prone to the initialization of the synapses too. So I come to the conclusions. I've shown that reinforcement learning is beneficial if you want to keep the resources in the infrastructure under control. For initialization, for me, it's clear that reinforcement learning can improve on the traditional approaches. So there is a 1-0 for reinforcement learning with respect to traditional approaches. For vertical scaling, I'm not so sure. There, the jury is still out to make a decision. So this is what I wanted to talk about today. If there are questions.
Thanks a lot, Danny, for a nice presentation and nice overview. And it was very interesting to see how reinforcement learning could be of benefit and in resource management in the system, and also how it is related to the classical methods.
Okay, thank you.
I see that already there is a question in the chat, so it would be great if you can return to the question later on. So
the question is,
and if there is any other question to raise, please feel free to do so. Otherwise, yeah, since we are a bit behind the schedule,
I will answer offline if that is okay.
Yeah, perfect.
And Danny, you are continuing to share your screen still.
Sorry.
By this, I would like to thanks Danny and all presenters so far. And I think we could have a relatively short break before continuing the rest of the session. So I would propose to start 3:35, so that we can continue with the rest of the program as it was scheduled. Let's see you all soon. Hello, everyone. Yeah, I think we are ready to continue in the session with the next seminar, which would be MARSAL project. So I would like to invite Panagiotis.
Hello, give me 1 second to share my slides.
Yeah, sure.
Okay.
Yes,
hope you can see now my slides.
We can see your slide clearly, and so we are.
Yeah, thank you.
Interested to see MARSAL view on.
Okay, I will close my camera for bandwidth purposes because here we don't have 5G. So
yeah, sure. we do the same.
Okay, so hi, I'm Panagiotis Kokkinos. I am from the Institute of Communication Computer System from Greece. This is a part of the work that the MARSAL project does, self-driven orchestration and intelligent management and communication storage, computational resources. So the motivation, of course, is that we need more and more resources, computing, storage, and network to serve popular online services, Internet of Things applications, smart city applications, etc. At the same time, we see that service providers push more and more content and data to the network edge. We also see that a lot of traffic flows start and finish within the city boundaries, so they don't live from the city boundaries. So in order to cope with all these requirements, we need networking, computing, and storage technologies and infrastructures that are deployed in the cities and interoperate. Regarding the edge, we all know that edge comes with various shapes and forms. We can have on-device or on-premise edge. We can have edge that is further from the data source or near the data source, or we can also have regional data centers that operate in the city boundaries. Regarding networks, again, the main inside the city, the main networking component segments are metropolitan networks, which are usually optical networks, and access networks that comes into forms, either wireless access networks or fixed wired optical networks, like passive optical networks. In any case, it is a clear requirement that we want to be able to manage this infrastructure, and we need to be able to programmably manage them in real time so as to advance services. So here is where the MARSAL project comes in. MARSAL is come from machine learning-based networking and computing infrastructure, resource management of 5G and beyond intelligent networks of the ICT-52 2020 call. Among others contributions, a MARSAL project proposes a new paradigm of elastic virtual infrastructure that targets exactly converged computing and storage and networking infrastructure. In practice, this what we call a virtual elastic infrastructure is in practice a network slice, which is composed of computing and network resources. And MARSAL, among other developments, of course, develops networking and computing management frameworks that are based on SDN and on cloud-native Kubernetes, which are coupled with intelligence for analyzing the monitoring data and for deciding about how to optimize or re-optimize the infrastructure and the resources in a closed loop form. So one of the challenges of the MARSAL is, as I said, to build this orchestration and logic. So in the logic part, we have network logic for deciding network-related configurations, computing logic for deciding the allocation of the computing and storage resources, and we also have a mechanism for collecting monitoring information and for analyzing this information. And then in the lower layer, in the second layer, we have the orchestration mechanisms. We have a SDN orchestration for a wired optical PON or point-to-point connections. We have the RIC for the wireless connections, and we have the compute and the cloud native controller for the regional edge and the radio edge resources. And also another challenge that we address in MARSAL is to implement this closed loop form control of computing and networking infrastructures. We need this closed loop control since application requirements and resource characteristics change continuously. So we want to have mechanisms that collect data, monitoring data, and then based on the collected data, they can provide load predictions, detect performance degradation of the various resources, provide recommendation actions, etc. And then based on these mechanisms, we can run proactively or reactively re-optimization adjustments in our infrastructure, both in our networking resources and our networking infrastructure and in our computing infrastructure. Next, we present a number of mechanisms, problems, to be honest, that we investigate. So we present the problems that we investigate, not the mechanisms that we use. So one of the problems that we investigate is the resource allocation of cloud native applications. So we assume that we have cloud native applications consisting of container-based microservices that have various computing and networking constraints and that can be represented by a graph. I remind you that containers are, package isolated environments that make easy to deploy and easy to migrate computing processing from one resource to another. So we develop resource allocation mechanisms for allocating microservices that represented like here in the figure, to allocate microservices to available resources while considering networking parameters, cost parameters. For example, we assume that edge resources are more expensive to use than cloud resources. So we consider these trade-offs. And also we develop these mechanisms are able to scale by migrating the components of the microservices of the containers, both vertically from one edge to another edge resource and horizontally from the edge to the cloud, so as to handle resource exhaustion or increase requirements from the applications. In the same context, another problem that we're investigating is the joint allocation of baseband and application workload. So we usually, there are a lot of works that consider the allocation of application workload in microservice form or in a bank of task form, whatever, in edge cloud continuum. And we also have a lot of works that consider the allocation of baseband processing in an edge cloud continuum, assuming that we have the baseband processing workload is divisible in CU, DUs, etc., and also that the application computing load is divisible. So what we investigating currently is how the scenario where we have an infrastructure that consisting of radio edge, regional edge, and cloud resources, where we have both application workloads and processing and baseband processing workloads. And the idea is how you can deploy these workloads in the various edge cloud continuum resources, while respecting, of course, the latency requirements that they have. We know that the baseband processing workloads, they have a lot of sensitive latency requirements. So the idea is how you can deploy all these workloads while taking into consideration these requirements. And of course, knowing that baseband processing workloads, of course, comes first from the respective application workloads. we assume that it may be possible to have edge resources that concurrently serve baseband and generic application workload. Another problem that we investigate is this, in continuation, of course, of what I just described, is this mobile edge computing for 5G and beyond 5G mobile networks. So we know that 5G and beyond utilize virtualization and edge computing. So since edge computing provides a lot of benefits, low latency, optimized network efficiency, reduced congestion. So, and also we have advanced and very interesting technologies in the wireless part. The optical part is more or less quite mature, many years now. While there are a lot of interesting developments in the wireless part. For example, we have these cell-free networks for the mobile access part of the network, where we assume that what they offer is the joint signal processing from many distributed access points. So having this in mind, we investigate the resource allocation for joint fiber wireless networks. So in this figure, we have access points that operate in a cell-free manner. So they cluster so as to serve particular users. We assume that we have massive MIMO base stations that communicate with the cell-free clusters. We have PON networks that carry this front haul traffic. And also we have resources, edge resources in the ONUs, in the DU, in the OLT part of the PON that serve baseband processing workloads. And so the question is how to jointly allocate the resources, how to cluster the access points, how to decide the settings of the massive MIMO antenna, how to decide the use of the PON, and how to allocate baseband processing workloads in DU and RU so as to efficiently serve the user demands, considering, of course, the available the capabilities of the infrastructure. Another problem that we investigate, and here we also present part of the idea that we use, is the machine learning-based event detection. So having an edge cloud continuum, we know that computing resources are subject to failures and subject to capacity exhaustion, for example, when an application scales too much. So we want to develop event detection mechanisms that are able to ping the orchestration mechanism so as to enable the implementation procedures. The novel idea that we use here is that we use knowledge graphs to present to represent the complexities of edge cloud continuum. So knowledge graphs represent a network of real-world entities and illustrate the relationships between them. So what we do is we use knowledge graphs to organize data from multiple sources. And then we apply graph embedding methods to transform these graph entities into vectors. And then we apply typical, more or less, machine learning anomaly detection mechanisms so as to, on this embedding, so as to detect events that relate to resource overusage. Finally, part of our contributions in the MARSAL project is that we are considering also and proposing an architecture, and we investigate the respective resource allocation problems. We propose what we name the data center in the city architecture. The idea is again the same, that we assume that we have a lot of traffic that goes from that it is inside the city from a user to another user, from a user to a computing or storage resource. And this is similar to the challenges of a data centers, where you have a lot of intra-data center traffic that you need to serve efficiently with low latency. So what we propose is that to identify areas in the metro network that we call metro islands that have a lot of high locality of traffic, and then create a physical or a virtual overlay network that interconnects efficiently these areas in the same way that, for example, inside the city, we built highways so as to reduce bottlenecks inside the city. And we explore various ideas, for example, using the filters technologies for metro islands. This idea, of course, have been applied in core networks for metro islands. And of course, for the overlays, we assume that we have SDN capabilities with WSSs, ROADMs, and receivers that are programmable. And for example, here we see that we have traffic coming from one metro island, and instead of going through the original network, it can utilize the overlay network that, as we assume that we have lower latency, higher capacity connections or reserved capacity connections, so as to move the traffic from one part of the city to another part of the city very efficiently. And of course, here we have a number of algorithm challenges. For example, deciding the nodes that act as the overlay gateway nodes, to also to dimension the metro islands capacity, the metro islands, to decide how large these metro islands will be, and also to place processing and data workloads respectively. For example, if we place workloads inside metro islands, then we assume that users can benefit from the locality. When we place workload and data in different metro islands, we assume that this can be served through efficiently through the overlay networks that we have built. So this is our part of what we currently see in the MARSAL project. We are in the last year of this project, and we have developed a lot of algorithms in cooperation with other partners, of course, that operate in this project. So that's all from my side. I don't know if you have any questions. I would be glad to answer it.
Thank you, Panagiotis, for sharing this insight from MARSAL project. As far as I see, there is no question in the chat. If there is any, please feel free to share it on the chat. So it's quite interesting to see how ML AI could contribute to new network topologies. For example, what you mentioned regarding the massive MIMO and also distributed MIMO, and how ML AI could be used there to reduce complexity. That's quite interesting insight, as well as in the other areas, and using knowledge-based graph for doing anomaly detection in the network. That's also something that show how ML AI could be used to increase the trust, security, and such kind of sustainability measures in the network or future networks. Very interesting insights. So,
thank you for the opportunity to present the results.
Is there any other questions or insight that anyone want to share on this? If not, I would like to invite Junyi Lee, Qualcomm Vice President, to share the insight from the Qualcomm side on intelligent networks and the path towards sustainable 6G. Junyi Lee, please.
Yes. Can you see the slides I'm sharing?
Yes, we see the slide clearly and we hear you very well.
Okay, thank you very much. Again, just like last speaker, to save the bandwidth, I try to turn off my camera, make sure that all the audio actually works well.
Sure.
All right. Thank you very much for the opportunity to share my thoughts on the path towards sustainable 6G. This slides graphically illustrate the transition for 5G to 6G from the perspective of 3GPP standardization. In the beginning of 2023, we are right in the middle of 5G evolution. The first big step of 5G, namely NR release 15 to 17, has completed in 3PP and led to the worldwide 5G deployment. The second wave of the 5G innovation, i.e. the release 18 to 20, referred to as 5G Advanced, will take the ecosystem through 2027. Even though the focus of the workshop and this talk is on 6G, we must recognize that a great amount of R&D effort has been and will be devoted to 5G Advanced, and that 6G will include both the evolution of these 5G Advanced technologies and more revolutionary ideas. As I will elaborate in the next few slides, the key market trends and technology drives that will lead the way to 6G are core technology advancements, environmental and societal sustainability, and the enhanced and new experiences. As a technologist, I'm very excited to see various core technology advance across many disciplines listed in these slides. As an example, new communication topology enable extreme network disaggregation that allows operator to flexibly mix and match various network components and services, and the new compute topology holistically partition compute and communication tasks to optimize latency, throughput, and power performance. Perception technologies lead to new human interface that connects the physical and the digital worlds. While 5G Advanced has started to study the use of AI/ML in wireless, 6G will consider AI/ML as a foundational technology for the wireless ecosystems. The goal of environmental and societal sustainability is that the ecosystems that connects people and things will deliver the services and products in a cost-effective way across all the regions globally. Specifically, the wireless ecosystem reached the few sustained global economy growth by adopting system design to minimize negative environmental impact and more accessible networks, devices, and services to promote digital equality. As mobile broadband continue to evolve, the technology can find new applications in fixed wireless, while the key benefit is easier deployment of wireless as opposed to wireline. Digital twins can more accurately model the physical world, therefore derive new values at the edge of the network. Merging the physical and the digital worlds enables new experiences in industry, medical, education, and entertainment. Similarly, metaverse augments the physical world with the virtual world and create new human interface, resulting in new type of devices beyond the smartphones, laptops, and watches that we are familiar with today. The key market trend and technology drives discussed in the previous few slides can be translated into a set of new engineering requirements that enable 6G to be a smarter wireless platform that to support enhanced services and new use case. You may recall that 5G consider a foundational triangle consists of enhanced mobile broadband, mission-critical services, and massive Internet of Things. The 6G platform will continue to evolve along those three dimensions to become next-generation broadband, real-time control, and pervasive access. In addition, 6G will consider three revolutionary dimensions, namely immersive platform and services, societal sustainability, and spatial perception. As a result of this new expansion of services and use case, 6G will require new capabilities beyond communications, which is viewed as the main capability in the previous generation of wireless technology. Those new capabilities including AI and compute, system resilience, integrated sensing, and green networks. Traditional KPI of communication include capacity, data rate, coverage, and so on. However, with non-communication capabilities, new KPIs will be needed for system design target. For AI and compute, we will be interested in inference accuracy, model transfer accuracy or latency, AI service round-trip time, compute capacity, as well as scalability and adaptability. To understand the KPI of system resilience, we need to consider security aspects such as confidentiality, integrity, availability, as well as mean time to detection, resolve, and contain security issues. The idea of integrated sensing is to leverage RF spectrum to not only deliver bits, but also sense the environment. The relevant KPIs will be range, confidence interval, sensing accuracy, resolution, and latency. Green network is about power and energy savings from the perspective of both devices and the networks. To satisfy the 6 foundational dimensions of service and use case of 6G, the above new KPIs lead to a diverse set of system requirements that will include evolutionary performance vectors such as capacity, data rate, and latency, and revolutionary dimensions such as user experience, positioning, capability, and ease of onboarding. To meet the 6 foundation, to meet the above 6 system requirement, we presented the following 6 key longer-term research vectors that will enable the path towards 6G. Specifically, use a data-driven approach to arrive at AI native end-to-end communication with joint training, model sharing, and distributed inference across networks and devices. Expand into new spectrum bands beyond millimeter waves and a new spectrum sharing paradigm with dynamic coordination assisted with environmental awareness. Develop scalable network architecture with disaggregated and virtualization and connect the intelligent edge and advanced topology. Merge the physical and digital and virtual world via ubiquitous low power joint sensing and communication. AI interface innovation include innovation of duplexing schemes, big MIMO, RIS, non-terrestrial networks, new waveforms, and coding modulation. Finally, various security aspects need to be addressed for communication resiliency. So let's look at those 6 vectors one by one in the next few slides. AI and wireless can really help each other. On one hand, advance in AI can definitely make wireless better. For example, by more efficiently utilize network resources. On the other hand, amplification of cellular can make AI better too. For example, a huge number of user devices can aggregate massive amount of data to improve AI models. The interplay between wireless and AI represent an effective paradigm to accelerate innovation in the 6G area. There are a variety of ways to evolve towards native wireless AI/ML. An overlay approach allows AI/ML to run independently at the device and network, enable proprietary ML procedure to be rapidly deployed. This can be done already in the 5G network. On the other hand, in the cross-node approach, currently being developed in 5G advanced, ML operates in a coordinated manner between the device and the network to achieve better performance. Finally, in a longer term, with native AI/ML in 6G, ML operates autonomously between the device and the network across all protocols and layers. Integrate ML procedure to train performance and adapt to different environments, fuse data for integrated dynamic machine learning lifecycle management. Recall that a major breakthrough of 5G is the use of millimeter wave spectrum for cellular communication. 6G will continue to expand into new spectrum territories to consider licensed, unlicensed, and shared spectrum. First, new upper middle band from 7 to 24 GHz brings orders of magnitude more wide area capacity as it combines the best of wide area coverage of sub-6 GHz and the wideband capacity of millimeter wave band. Second, building on the solid foundation of 5G NR, we can continue to expand and enhance mobile millimeter wave technology in the key area of coverage, beam management, device size and power, robustness, and topology enhancements. Third, looking in a longer term, sub-terahertz spectrum is a big, viable opportunity for communication and beyond. Sub-terahertz is probably not a wide area spectrum. However, given the huge amount of spectrum, sub-terahertz can unlock new and enhanced user experience. For example, the new use case such as wireless front hall, data center, high resolution sensing and positioning. We will build on our millimeter wave experience to address key system challenges at higher band spectrum. Finally, spectrum sharings enhance the utilization of spectrum. We will build on 4G, 5G spectrum innovation to evolve towards licensed spectrum shared for improved efficiency, flexibility, and user experience in 6G. In addition to spectrum sharing, we will also consider network equipment sharing. For example, O-RAN has developed architecture to allow operator to cost-effectively offer services differentiations, e.g. through radio unit RU sharing. Spectrum sharing and sensing is one area that one can greatly leverage AI/ML. The third vector is about new use cases, especially augmented reality and virtual reality, AI and VR, for both enterprise and consumer. Digital twin model complex physical world, while spatial computing enables immersive interaction with 3D digital content. All of this will impose much more stringent requirements on the communication capabilities than typical eMBB in terms of capacity, latency, reliability, as well as power and thermal. To meet the requirement of XR, 6G protocols will natively support distributed compute to holistically optimize compute and communication. For example, dynamically distributed workload among different nodes in the network. The fourth vector is about joint communication and non-communication capabilities, such as RF positioning, sensing, and power transfer. This is a great example of utilizing existing waveform and other physical layer design, spectrum, and network infrastructure for new type of services beyond delivering bits. The core of any new generation of wireless communication must look closely at the fundamentals of the air interface design in the areas of waveform, coding modulation, and multiple access schemes. A large body of research has been devoted to various physical layer topics. Here, I don't have time to elaborate too much on this. Next, we are moving up to the protocol stack. Evolving network architecture driven by disaggregation and cloudification of tiered service is a key vector of 6G technology development. In particular, 6G will drive diverse deployment, topology, and technology. The picture shows a variety of network nodes, such as a microcell, integrated access backhaul IAB nodes, simple as well as smart repeaters that we use here, and also use distributed massive MIMO, use radio unit, low side unit, even low side unit that people develop in a CV2X context, as well as a new type of technology such as intelligent service and the reconfigurable intelligent service. RIS is a very good example that certain technology which is not available 10 years ago, but become expect to play a critical role in 6G. Looking beyond terrestrial communication, non-terrestrial communications, including UAV, HAPS, satellites can greatly complement traditional terrestrial communication. Finally, 6G can address the security and privacy aspect across all the layers, building on the proven solid security foundation of 5G. This aspect is especially important for system resiliency. Thanks everyone for listening to this presentation. This concludes my talk.
Thank you, Junyi, for your very insightful and comprehensive presentation of this topic, of different technology components that could shape 6G. And as we have seen, that there seems lots of synergy between the technologies that you have envisioned and the different components that has been covered in today and yesterday talks in different European projects. So there is lots of synergy and commonalities. So far, I don't see any question in the chat. So if there is any question, please raise the question.
Maybe I would have then one question that, yeah, thanks a lot, Junyi and Qualcomm for the presentation, so great material. With respect to this AI, which is especially the main focus of most of the presentations in this session, so do you see that there would be much of difference in the approach among the different players in AI, or would you rather see that it's going to rather same direction? And do you think that how optimistic are you with respect to AI for 6G? How fundamental effect will it have in the end?
I think that is a very good question, and you know, because we already in release 18 in CPP, we already started some discussions among different companies of, and mostly at this point we are more like setting up the framework, right, in terms of how we manage the model life cycles, how you evaluate this kind of evaluation methodology. From that perspective, I strongly feel that although people maybe have different opinions of some of the details, terminologies, but the overall directions, I think there's a lot of synergies, that among different companies of how we want to build towards AI native technologies in a long run. Right? So although on the 5G part on release 18, we are still addressing relatively short-term things to set up the stage. But I think that in the long run, a lot of companies have very similar views of what we can do. Yeah.
Thank you.
So yeah, towards the path towards the AI native system, it was interesting vision that you have shared regarding the cooperation between the device side and also the network side, and it seems that it need to be kind of like multi-stage developments that we could start from. Possibly they could start from like independent ML AI models, but then in the later stage we could go further collaboration between network and device side, and so that's
totally. I mean that. Yeah, totally agree with that. I mean, the network, including the LAN type of base station and network, as well as even the third party, right? If people have a better idea of, over the top, they can also provide some kind of plug-in approach, and then we can test out the result. So like the key part is actually is not only develop a model, share the data training, but also how you evaluate the performance of different models in different environment, right? Because those kind of performance will heavily depends on the environment. So.
And regarding the air interface design, how much do you think the AI would have a role in that area specifically?
I would say that in the past, we at Qualcomm we did our own study, but also that's a huge amount of studies in industry, academia, people looking into all different aspects. If you look at the physical layer, right? People even look at it more fundamentally. So say, can I just get rid of all the coding, decoding, more like a completely AI native communication scheme, and then they show very very good performance indeed, right? So of course we have to balance in terms of the complexity, especially on the UE side, the complexity, the thermal, the power, right? So the complexity of AI versus like more traditional, more very much optimized coding decoding performance. But overall, I feel that there's lots of good progress on that. For example, people develop AI, use AI to develop non-uniform constellation, right? So that actually can, achieve pretty good performance in terms of power, especially given the complexity of PA, right? We have to deal with nonlinear PA. So in terms of nonlinear PA, what modulation makes sense? So often people think about using non-uniform modulation to deal with nonlinear PA, but what is optimal form? It's not very easy to do. But AI, from that perspective, can provide a very good insight.
Yeah, very interesting and very interesting synergies between this region and also what we have been working on in different European projects. In particular, Hexa-X was also looking at this topic. I would like to thank you so much for a very nice presentation, a very nice discussion, and sharing the insights. If there is no further question, we may move to the next seminar.
Thanks, everyone.
Thank you. So our next seminar is from China Mobile, Dr. Guangyi Liu, Chief Scientist of 6G from China Mobile. Please.
Thank you. So can you see my screen?
We can see you, but not your slide yet.
Okay. Let me try. Okay. Can you see it?
Yes, we can see your slide clearly. Yeah.
Okay.
Here you
go.
go.
Okay. Thank you very much for Miko to invite me to have this presentation here. Today, I'd like to talk to you about the 6G network is native AI, evolved from the AI for network to network to AI for network. First, let me talk about the driving forces for the native AI. As you know, towards the year 2030, we do believe we will have not just a physical world, but also we will have a digital world and build up a digital twin world. So based on such kind of a digital twin, of course, we can not just simulate, but also predict the future of the physical world's future development. And also we can even provide some intervention in advance to keep the physical world be on track. That means we can not just sense the network, sense the current world, but also we can change the future.
So, sorry, Guangyi Liu, did you move to second slide? Because I can see only the title slide still.
Can you see that?
Only the title slide. At least Mikko can see only that one. But
I don't. Oh, okay. Maybe I can just switch off my camera and let's see if we can see.
We don't see them in a full screen. So if you share them in full screen, we cannot see them.
And now there is slide number 4.
Is it okay now? It's full screen from my side.
It is on a slide number 4 now. So.
Okay.
But
okay, so I continue my presentation. So, and also based on the digital world, of course, we can have enough data to support the AI's application anywhere, anytime, and give us the ubiquitous intelligence. So, based on such an atmosphere, of course, we can identify many use cases for AI from the human, from the vertical industry, and also from network autonomy aspects. To fulfill all these use cases demands on the AI's capabilities, of course, we need change the current AI's design for the network. We need to support the native design to provide the necessary data and also the computing power, and of course the algorithm and model of the AI anywhere, anytime, and also can guarantee the AI service quality during the entire life cycle. So from this perspective, we do believe for 6G network, of course, we will not just define the traditional communication KPIs, but also we need the more dimension to cover more new capabilities of the network, like the AI, like security and computing, and of course the sensing. So in our mind, we do believe 6G mobile network will look like this. At the bottom layer is the physical infrastructure layer. It includes the traditional antenna, AAU, RU, etc., and also the edge cloud and centric cloud to provide the computing and storage. Above the physical infrastructure layer is the logical function layer, where the network function is deployed in the edge cloud or in the central cloud, and to set up the capabilities like the communication, big data, computing, AI security, etc., and to serve for the very diverse and differentiated use cases from our physical world. So for 6G, we do believe it will be a new generation mobile information network, which will integrate the communication, computing, big data, AI, sensing, and security, etc., and provide a platform to serve our customer in an on-demand way for the for all kinds of services. So how in previous part I have mentioned the driving forces necessary for the native AI. So how to really achieve the native AI design for the 6G mobile network? From our side, we do believe this is evolve from the AI for network to network for AI. First, since we already have a very good practice on the AI application in current 5G network.
Excuse me. So we are still see your slide number 4. Is it just
really?
confirmed? Is it the correct one? Yes.
Oh, sorry. I don't know what's exactly the problem. I just use the web page to. Let me try again.
Yeah, please share.
Guangyi, if you make it full screen, switch back to the window and share the full screen application, not the windowed application. It appears as a secondary application once it's in full screen.
Okay. Does that work this time?
Yeah, we just saw it in full screen for a short moment. Yes, now we see it in full screen. So
okay, so it's okay.
Yes, can you navigate forward and back to just make sure it's working?
Okay, let me see. Is it work?
Yes.
Okay, thank you.
Thanks.
Just we have good practice on the AI application in 5G network. We can have some findings for further consideration for the native AI. As you know, typically for the AI's introduction to the 5G network, especially for the AI for network use cases, we can see typically there's 2 modes. The first one, of course, is a server with the AI resources is connected to the network management equipment. And thus, the AI service can be introduced to the network, especially for the network management in a case-driven way. The second mode is we can also add some new network elements to the network. For example, here, NWDF to provide the data analysis. However, Since at the beginning of the network architecture design, we never consider the AI's application in the network. So it provides a constraint on the data availability and the data acquisition latency, and also the data's consistency and also conformance, which will also degrade the performance of the AI application as we expected. So based on such practice, we do see we have some findings from 5G intelligent network, especially to achieve better performance for the AI's application. First, we need a unified framework to achieve a fully automatic closed loop of AI's pre-validation, online evaluation, and also the optimization for the algorithm and the model. Second, we need the efficient data acquisition and the transmission, because it's really a headache for the current application of the AI, especially for some in-time or instant application of the AI's use cases. The third one is we need the integration of computing data models and also the connections to provide the guaranteed quality of the service. For example, the even lower latency, which cannot be guaranteed by the current AI's use cases for 5G network. Second, we also see we already have a very successful AI application outside of the mobile network. We termed it as a cloud AI service providing. From such kind of usage scenarios, we can see the cloud AI service only can provide the best effort AI services after users submit orders. Typically, in such cases, the mobile network is considered as a transparent pipe only. Then, so the context of the mobile network cannot be considered for the especially for the optimization of the AI's performance from the cloud provider perspective, and also for such kind of service providing. For such kind of service providing way, we do also see the problem of the data privacy and the data security, since the customer have to submit upload all the data to the cloud. And in such way, it will have the problem for the data privacy and security aspects. So from such kind of practice, we do see to further achieve better performance, of course, we need to fully utilize the AI-related resource of the network, especially when we consider the coordination or cooperation between the devices, their terminal, and the network. We do need to consider the air interface's impact on the performance. And also we need to provide the guaranteed quality of service for the AI, because just as I have mentioned before, for the current cloud AI service, we can only provide the best effort service to our customer. Third one, of course, is to further cover more and more use cases of the AI. Of course, we need to protect the data privacy and the security, as will be the key for AI application for in future. So for the native AI's design, we have identified some very important principles which have to be considered for the network architecture's design. First, we need to not just the network AI's design will not just cover the use cases of the network operation and the maintenance itself, but also it should cover the use cases outside of the network. We termed it as the AI for network use cases, like the industrial, internet, smart power, smart agriculture, internet of vehicle, etc. Second, I think the design of the AI should evolve from external and patched way to the native and integrated way. That means we can, for the native AI's design, we need to provide the necessary resources like the data, like the computing power, like the algorithm and model, which is demanded by the individual AI's use cases. And third, of course, we should evolve from the best effort way to the QoS guaranteed way. That means only by this way we can provide the diverse and differentiated service quality to serve for the individual use cases of AI for all the use cases. So since we have regarding the communication regarding the protocol design, we have to consider how we can guarantee the AI service. If we really want to enable the AI as a service, we need to consider how to provide the quality service guarantee procedure in an end-to-end way, just like the traditional communication services we have achieved in the legacy mobile network. If we look at the traditional mobile communication network, we can see it has set up an entire end-to-end protocols to guarantee the service, the resource scaling, and also the quality evaluation, and also the quality guarantee for the during the entire life cycle of these communication services. So similar design can also be introduced to guarantee the AI's service quality. Here, for example, I just show you an example we have considered. Besides the traditional communication plan, the data plan are introduced to acquire the data necessary for the AI's application, and also it can also provide the storage, the pre-processing of the data, and also provided data for the other use cases. And also the computing plan is introduced to provide the computing power for the AI's use cases supporting. And also the intelligence plan is introduced to provide the end-to-end quality of service guarantee, and also the provided the necessary resources of like the AI model and AI algorithms, and thus can provide end-to-end service quality guarantee like the traditional communication services in the legacy network, mobile network. From the functional design perspective, especially for the native AI framework, we do believe we need to provide the necessary necessary resources from like the model, like the computing power, like the data which is demanded by some individual use cases. So at least we do believe the whole framework for the native AI at least should include 4 parts, like the AI use cases self-generation, the QoS guarantee mechanism, and also the entire life cycle AI workflow management, and also the on-demand scheduling of the multi-dimensional resources I have mentioned before. Here, this picture just shows you an example we have published in some paper. Based on the user demand, the mobile network can generate or import the AI service requirements, and then it can be interpreted or mapped to the AI's QoS, and then it is expand on all the schedule to the corresponding AI model, algorithm, and computing power, and also the data demanded for the application to serve for the AI's use cases. And during the serving procedure, the AI quality of the service of the AI application will be evaluated timely, and the results can be used to dynamically change the optimization strategy for the scheduling of the multi-dimensional resources for the algorithm module and computing power, and also the data, and thus can achieve the quality guaranteed for the entire life cycle. For the AI frameworks design, of course, there's several issues we need to be addressed in future study. Like the first one is is about the self-generation of the AI use cases. As you know, currently we don't have the matured description for different use cases, especially especially now, I think we have some examples like here in table 2, but we are not sure if it is enough to cover some other type of the use cases. So for future study, we do need to study how to design the description, especially for different use cases, and also how to design the efficient acquisition and the storage and the governance, and also the transportation of the data necessary for the AI application and support the AI use cases self-generation. The issue 2 is how to define the quality of the AI services and how to guarantee it during the entire life cycle of the AI application. Currently, I think we have some examples. Just show you here the definition of the some performance indicators for the AI training services. For example, the performance, overhead, safety, privacy, and etc. And also, in Figure 1 we have also defined some procedures for the task flows service, and try to, by this way, we can try to provide the guarantee mechanism for the QoAIS. And also for further study, we also are facing a few challenges, like how to provide the quantitative evaluation method for some indicators like the generalization, interpretability, etc. for the AI use cases. And also how to realize the automatic analysis and the mapping of the AI service requirements to the QoAIS indicators, as also will be the key for us to open the door for the guarantee of the AI services quality. Issue 3 is the life cycle orchestration and management of the AI services. For the current 5G, most of the AI workflows are implemented offline and independent from network operation environments. That's lead to the low efficiency and the higher cost, especially it cannot provide the environment to pre-validate the performance of the AI model algorithms, and thus can degrade the performance for the AI application. So for 6G, its target is to provide a complete operation environment for all the aspects of the end-to-end AI workflow, and not just the data, not just the algorithm model and also the computing power, but also can provide an environment and for the pre-validation and also the evaluation of the quality of the service, etc. Here, the left hand just show you example of our design. The one AI use case and all AI service will be interpreted and all decoupled as multiple AI workflows, and each workflows can be guaranteed, can be served with the guaranteed quality of the service, and then the quality of service of the AI, the entire AI service can be guaranteed. And also in the right hand, just show you AI orchestration and life procedures for during the life cycle. For example, here just show you based on the requirements from the use cases, as the data management can provide the necessary data for the model training, and then the model training procedure can provide the trained model, and then the model can be pre-validated in the operation environment, and then it is deployed and for the practical use cases, and then the data can be connected from the use cases and returned to the data management for further use of the, for example, the tuning, the further optimization of the model itself. For this issue, we also need to consider how to design the different protocol, especially the data plan, control plan, and the AI plan together with traditional communication plan, and also how to design the open AI capability interface for different use cases is also a challenge for further study. The issue 4, of course, is the joint optimization of the communication and also the computing for the AI application. For the traditional 5G mobile computing, you can see the communication and computing are loosely coupled. It is designed like the option 1. They are designed independently. But for the native AI, it really requires the higher performance and high power efficiency and low latency for the computing. So the integration or the joint optimization of the communication and the computing protocol is very important. Just using this picture, we can have different options. Like the option 1 is just loosely coupled, and option 2 it have some interaction between the radio resource control and also the computing resource control. And also, of course, option 3 can have really integrated design for the protocol of the resource radio resource and the computing resource control. So typically for the AI service of the 6G network, it cannot just only provide the complete AI service for the entire life cycle, but also it can put part of the AI service procedure, like provide the data model training, inference, and also can provide the service of the verification of the AI model and the algorithms. Finally, I just give you a brief summary. For 6G, we do believe native AI will target to guarantee the quality of the service of the AI use cases by providing the sources of the data acquisition model and also computing power in an on-demand way. And thus, it can help us to not just explore the AI application for the network, but also can provide the AI services for the use cases outside of the mobile network. To really achieve this, of course, we do believe many future research is necessary, like the SLA and quality of service, AI service requirements guarantee, and also the deeper integration of multidimensional resources I have mentioned before, the computing, the communication, and also even the data, etc. And also the security and the privacy guarantee is also very important for us to really explore the new use cases for AI. For the more details, please refer to our white papers we have published in February last year. And also, as you know, to really push the work on the network AI or AI as a service, we have initiated a 6G Alliance of the Network AI. We termed it as the 6G ANA in November year 2020. The role of the 6G ANA is to provide a domestic official platform for the study of the network AI for 6G and to promote the AI as a service by native AI design from the technology and ecosystem perspective. And also, 6G ANA is like to organize the members to study the relevant issues of the network AI, and also try to build up the consensus and promote its standardization and the industrialization for future. And we have also for the 6G ANA, its organization looks like this. We have an advisory group, we have technical steering committee, and also we have set up 7 technical working groups, like we have just shown this picture. And also by now we have more than 30 members being involved in the activities, not just the members from China, but also from UK and from some other countries. And here I think I'm very happy to invite all you involved in today's workshop to join us on the network AI activity and try to push it to be true in 6G network in near future. And also we have published several white papers since December year 2020, and the more details can be found in this web page. That's all my presentations. Thank you.
Thank you very much for sharing the insight from the operator side on AI as a service. So it was very insightful. So it's interesting that you see that AI as a service would be kind of evolution from like best effort towards guaranteed quality of services, and to guarantee quality of service, it seems there need to be a process, and so it's the networks would evolve towards that. And also it was interesting to see that AI as a service is not, would cover different type of services in the AI domain. So it would not be only a single service, so it would be kind of like a portfolio of different type of services as you have shared. As far as I see, there is no immediate question, but if there is any question, please raise it in the chat or just ask. I think we have 1 minute to. And it was very interesting to share kind of like challenges that we are facing towards having AI as a service, as you pointed out. So if there is no further question, so I would like to thank you.
Thank you. It's my pleasure
for your presentation, and we can continue with AI at Edge project, where Niva will share the insights.
Yes, thank you, Hamed. I will share my screens. Can you hear me? Do you see?
Yes, it is clear.
Great. Thank you so much. Good afternoon, everybody. My name is Neva Linder. I work as a research leader in the area of network management and automation at Ericsson Research in Sweden, in Stockholm. Here a colleague from Hamed as well. But today I'm here representing the AI at Edge as the Work Package 2 leader on architecture. As a glance, AI at Edge stands for a secure and reusable AI platform for edge computing in beyond 5G networks. Some key figures from us: we are entering right now our 3rd year of work, so we already have some deliverables out, but it's still like the closure. We still have a lot of interesting work to develop and show for this year. And we are in total 20 partners, half academia, half SMEs and industries. Some expected breakthroughs here for AI at Edge. We also believe in AI for networks and network for AI. And we do study how we can have our networks building up and designed for AI-enabled applications. We explore connected compute platform, thinking on orchestration, sales management and orchestration. We explore hardware accelerated serverless platform for AI, and also not least on network automation, closed loop automation, thinking on a multi-stakeholder, multi-vendor environment. But in the ground, my presentation is about actually if we in some sense need more automation telecom, or if AI automation cloud, we are talking just about buzzwords. And to comment on that, I also along the presentation we share some of the AI at Edge architecture challenge that we have been facing. Thinking that in an ideal case we would have a native edge, but what we see right now is it's pretty much AI silos and for tools, execution environments, and for the data, how we resolve observability. And even from the principle, what do we mean by AI native and an AI native architecture? Do we fully understand that? I'll comment about that as well. And to get started here, just to thinking on how do we see from where we come from, right? One telecom network, and then a voice serves, and then coming from voice data, video data, and how we see now what we want to see 6G and ever-present intelligent communications. So new applications, new domains, one network, and what we see in practice is that we are hiring absolutely since 5G, increasing the complexity of the network operations, a service, even like time to market, service deployment, how we deal with and the service assurance also of all of those different services. And then we see clearly an OPEX or complexity along the Gs, and this a curve, exponential curve. For AI at the edge, we have chosen 4 particular use cases to also test these, validate, contribute to KPIs. But in some sense, what we want is actually that we want to understand the key technology enablers like cloud, automation, AI, and actually use those. We believe that there are already indications that we can simplify operations on networks using, for example, AI-based automation. And the need here highlights to really break this curve, break this trend, and be able to handle complexity, scalability of services, applications, operations in a competitive cost. And of course, with these new services, new verticals entering, and the telco words, that we can have new business models also. And here the wish that we should place a 6G below this curve here. Let's handle complexity. But coming back with the AI at the edge, so these are the test beds at a glance. So we have remote driving cars, we have the industrial IoT use case, also drones flying beyond line of sight, and also smart entertainment for flight. So we decided as a consortium to have a real test beds, so we can talk about collecting data, studying proof points, our algorithms, and having integration, validation of KPIs, and doing the technical economic analysis. And I can say that what they have in common is, for example, when we talk about integration, to have a common core networks of functionalities, and also test up scalability of, for example, Mueck solutions for orchestration. But we started in some sense in a conceptual architecture, and thinking also in an AI function that we call it. So we here have basically a service management orchestration layer, we call it NSAP, and a connect compute platform for orchestration. This deployment use case, radio access site or far edge, near edge cloud. We have this concept in mind, and of course is the slices, but then having in mind that we need to deal with latency critical AIFs, both for network functions and applications. And then we have low latency AIFs, so latency tolerance. So different here, really time frames. And with that, as said, we the AI at edge went deeper in considering the IFs in the sense to have an AI model encapsulated in a cloud native function, containerized, and with different interfaces, how this would look like. Also, as a requirement, what we need to have, it's an end-to-end network data infrastructure that can support those IFs, with observability, so data collection, how we do a real ingestion, data ingestion architecture, collect once, and keep what is relevant, exposure as on demand, but also even further that we have not only data, but that we can provide on AI ML model lifecycle management to have from the deployment to check in what is the performance of a model, it is still valid, and so on. Actually, the model lifecycle management, that pipeline is that we will further explore also this year with more implementation. But then if we think about having an analogy here, since we're talking about cloud and also AI, we have been, the industry is more mature now on understanding what are cloud native. So understand the need for microservices, DevOps, CI/CD containers. And then we can, in order to define what would be a AI native architecture, we can have also state that, yes, we need intelligence everywhere, but it would be quite similar to what we talk about MLOps, a distributed data infrastructure, that this all is managed in an effective way in a zero-touch automation. And the AI service and exposure of AI service is important. I have seen some mentioning here. It's still like a kind of option. We are starting to understand. But having thinking on design, what in some sense what we want is that to come from using AI to what we call an AI native. So in a general way, if you have a domain, not specifically telco, but a domain, we have several layers. What we do now, it's using specifically AIs for specific applications or services, but they are isolated. They collect once and be in silos. What we want to evolve our telco network is that those AI/ML models, they can use a common data-driven infrastructure and hopefully in a cross-domain, so that data observability is collected once, that we have a common execution environment, and then we can scale in terms not only in applications but in network functions. And then eventually, what we are talking 6G here, when this is really empowered, allowed, enabled to having, for example, closed loops between multiple layers and a mature, not only data-driven infrastructure, but a mature model orchestration cross-domain. And with that in mind, that I can here at a glance show how we in AI at the edge we have been working toward a sort of what we believe a consolidated architecture that will enable AI at edge, but also in an end-to-end network, independent of use case. But here, what we have done is to work in this network service automation platform. We are not implementing all the components, but what we are doing is that we are highlighting the capability that we believe are fundamental to really realize and support AI at edge. And here we agree on evolution of service-based bus here with end-to-end mature data-driven architecture with AI/ML and lifecycle management. Here, very important connect compute platform. So here we see not only the management layer, but next systems, also in 5G systems, core components, but in particular, in terms of intelligent networks, what we are exploring, it is one of the novelties of the project, is to have interfaces like for a multi-tier orchestrator to a Mueck app, IF orchestrator here for the edge. And so IFs as Mueck applications, how these would look like, and also, as I mentioned, hardware acceleration on that. So I invite all of you for our to check our deliveries on architecture. I mentioned this. Well, I can mention that in particular the part of exposure, right? To have not only the RAPs and R1 here exposure, but also to have other data sources and a sort of service management exposure, data management exposure. And not least, very important, we believe that's not only for run, right? So it run core also over the end-to-end network. A bit more on the orchestration side, I said we have this at least 2 levels of orchestration on the NSOP level and in the Mueck. So we extend here that Mueck interfaces, and for the IFs functionalities like onboarding, deployment, internal external integration, termination, those we are working on the workflows and implementation also on those. New interface that project bring on, as I mentioned, between the orchestrations and also connecting the NSAP to the Connect Compute platform. And here, since I'm talking, as I talk more about the network automation, because we are developing specific methods and algorithms for network automation, And I bring here from them 2 sets where we have predictive resource monitoring for service placement, end-to-end, but also on the edge. And I can highlight as well solutions for advanced support and AI-enabled applications for anomaly detection using different learners, like, for example, federated learning. I selected 3 works about that, and that I can give the reference, and but just pointing out, picking up here some flavors. And so AIF placement in federated learning environments. Here, for example, the proposal is to model the placement problem with a mixed linear problem, and therefore how many IEFs to be deployed where in each node. All right, and then considering here learn and inference time targets, and showing how the hardware accelerated can be used to reduce a prolonged learning time. So that's when you are differently from if you train your model in previously and kind of deploy, but then you do this training or updating, retraining on the architecture on the network. Right? So I do recommend that. Another example, if you have the AI applications, specifically serves for anomaly detection, and we want, for example, to reduce learning time, and ensure that you don't need to move the data from the edge nodes. Then we can think about in such solution to guarantee low latency processing and scale, and also trade this learning time reduction and detection kind of accuracy. But in this case, for anomaly detection of networks. And I can tell you that one thing is that you use methods to detect that something happened. Predict as well. But one other thing is, of course, to attempt to understand and have a root cause analysis. So this work has been done as well. I believe this is a problem still for the networks, how to do this monitoring, and here in different layers, try to also, then you have kind of really the closed loop, so you do not only predict the problem, but then you can also detect what is the root cause, and hopefully prevent this to happen, because well, if something happened, it might be that you can just restart your servers, your computers, but then understand what is the root, that's another thing. And these were some flavors, I think, that I brought to you in terms of the work that we are doing on the IIT Edge. Yes, I hope that we understand now that we need more automation for sure, and then we are not talk hopefully about busy words. There is still a lot of work to be done in terms of the AI native architecture, and we are starting to understand that. And the IIT Edge is hopefully providing some good contributions and to the community about that. And with that, I thank you. And do we have any questions?
Thank you so much, Eva, for sharing the insight from AI Edge project. It was quite interesting that you shared that AI technology is something that possibly we could rely to enable the demanding 6G new use cases, while at the same time we could maintain a good level of complexity in the network. And from that perspective, it seems that AI is not something luxury to have in the network, but somehow a necessity to cope with that demand. Is it right understanding?
Yes, it's a good way to cope. We already understand in terms of optimization, but Also, in terms of in a macro end-to-end networks, the network operations are scaling, and yeah, we need to deal with this to really fully deploy 6G.
So and then how is the region, whether considering the new use cases that are appearing, like sensing, XR, VR, and so on, and as you mentioned, the complexity are increasing. Is there some insight that AI could be able to cope and manage the complexity in the networks, or where we are standing there?
I think that we are collecting our understanding on our now deployments in the 5G also. And so, I mean, we see like 6G like pushing really the barriers, but even now today in our networks. And so, and here I can highlight even not only net operations of services that are already deployed, but even the time to market, it's complex. So to really deploy a new service, we can talk about months. And how we do reduce this, and then AI ML-based automation is really going to be a tool that are helping us to deal with such complexity. And hopefully will be mature already for the 6G.
Yeah, thank you. So promising. Mm-hmm. So there is already questions in the chat. So if you can go through it, we are slightly over time, but
okay, I can attempt. So Arthur, I presume that you have several edge sites implementing some AI. How do you plan to find the suitable best edge sites? What do you do in case the movement, load, change, etc.? There is no one answer fits all, right? But here there is a. So you need to have a kind of a knowledge of your, of course, a network, some kind of discovery or monitoring and so forth. But then, for example, where to have these the IEFs in this case deployed, or MEC apps or so forth. So there are this is yeah, the displacement that you're talking about is still a research problem, and of course where the models, what are the nodes? You need to, I mean, the network should self-discover. That's part of the problem. Where you can, for example, have nodes with processing capabilities to do inference or even retrain. So that's, yeah, it's an interesting area to do research.
Yeah, thank you, Neva.
Thank you.
I would like to thank you and all presenters in today's session. So it was very insightful to see all the innovations that are happening in this domain. So today we have seen that AI and ML techniques could and would have a critical role in optimizing and improving different functionalities in the networks. We have seen works from physical layer domain, also network domain, and also management, and also we have seen that how future 6G networks would enable AI services and different type of AI services. And also we have seen that the development in either of these domains seems to be kind of like evolution that we need to and a process to work on, and there is lots of innovation opportunities. Already we have seen various type of innovations in the European projects and also globally in regional innovations in Asia and also in US. Yeah, we are looking forward to the development in this domain, and please share, please follow the deliverables of these different ICT-52 projects in this topic and also other topics. And by this, I would like to thank everyone that contributed to these seminars through presentation or discussions. And yeah, I would like to thanks everyone. if Mikko, you have any remarks to share before we close the session.
You made a good concluding statements already. So yes, on my behalf as well, thank you to everybody for active participation, especially to presenters. And for the 2 days, 4 sessions, as said, we are collecting the presentations to share them as well as the videos.
Yeah. Thank you. So the videos and then the slides will be available later on Hexa-X website on the page of this event. Yeah. So I think we can close the events if there is no further comments or question. Yeah, by this, yeah, we can say goodbye and thanks everyone.
Yeah, thank you.
Bye.
Thank you.
Thank you
very much.